All right, we'll get back to section 4.1 and 4.2. We're solving exponential equations now. This is going to be important for later on when you're going to be solving some more exponential equations, but also it's going to be important for kind of talking more about logarithms when we get there. So in these problems, we have an exponential equation, and you're going to use the statement that says if a to the u equals a to the v, then u is equal to the v. Okay, so if the base is the same on both sides, you can get rid of the base and set the powers equal. Okay, so what if I want to solve the equation 3 to the power of 3x minus 2 equals 81? Well, 81, that's the same as 3 to the 4th power, right? 3 times 3 times 3 times 3. And now that I got the same base on both sides, I can remove those 3's and set the powers equal. So I got 3x minus 2 equals 4, or 3x equals 6. That means that x equals 2. Okay? Now you don't need to bother checking your answers if you don't want. You're not going to have extraneous solutions here with this kind. Of course you can, check the answers if you want. So if x is 2, 3 times 2 is 6, minus 2 is 4. 3 to the 4th, yeah, that's 81, okay? Here's another example. So what if we want to solve 4 to the power 3x minus 1 equals 32 to the power x plus 2? Solve for x. Okay, so with this problem, 32 is not a power of 4. In other words, 4 to the first is 4. 4 squared is 16. 4 cubed, 4 times 4 times 4, that's 64. Okay, so in this problem, I'm going to have to change both bases on each side there. We'll get base 2 on each side. So 2 squared, that's the same as 4. And 2 to the 5th power is the same as 32, right? If I take 2 times 2 times 2 times 2 times 2, I get 32. And by my rules of exponents here, so I'm using the law number 3 here, I'm supposed to multiply these powers. Okay, so 2 times 3x minus 1, that's going to be 6x minus 2. 5 times x plus 2, that's 5x plus 10. I have the same base 2. And yes, I can remove the 2's and set the powers equal. Looks like 6x minus 2 equals 5x plus 10. And if I subtract 5x from both sides, and then add 2 to both sides, x is 12. Okay, so 12 is going to be the answer there. Now the point of that one is to say that, sometimes with these equations, like you'll have to, change up both sides, not just one side. Okay. Let's try another one. So how about, what if I had the equation e to the power negative x squared equals e to the x squared times 1 over e cubed. E meaning the number e that we talked about in the last video. So, well, I want to solve for x. Okay. Now, e to the x squared, again, using law 3, there, I'm supposed to multiply the powers. So that's the same as e to the 2x. Times 1 over e cubed, that's the same as e to the negative 3rd power. Okay, and then using law 1, I have the same base, right? So I can add the powers there. Okay, so e to the 2x times e to the negative 3rd power, that's the same as e to the 2x minus 3 power. And now I got the same base e on both sides, so I can remove the e's and set the powers equal. So negative x squared equals 2x minus 3. And that means that x squared plus 2x minus 3 equals 0. Okay, that's a quadratic equation. And that one's going to factor nicely as x plus 3 times x minus 1. Okay, so then the next thing would be to, I get x equals -3 and x equals 1. And those are the two solutions there. Okay. Here's another example. So what if I wanted to solve 5 to the power -3x plus 9 equals 1? Solve for x. Okay, well 1 is the same thing as 5 to the 0, right? Anything to the 0 power is 1. And I'm trying to get the same base on both sides. I have that now. I can remove the 5's and set the powers equal. -3x plus 9 equals 0 means that if you subtract 9 and then divide by -3, x equals 3. Okay. Now, there's a worksheet here that I would like you to look at where you're solving exponential equations. And I have 25 problems on this worksheet here. And then I've also got the answers to all those problems. And that's going to be really important to look over, okay? Because, again, to fully understand what's going on with logarithms, I feel like you have to know how to solve an exponential equation. And we'll get there. Like, so in the next section, you know, we're gonna introduce logarithms. Okay. So be sure to look at the homework that's on that worksheet there. Okay, when you get a chance. The next thing is I have some story problems in this section that I'd like us to look over. So let's see. The first one deals with compound interest. Compound interest is interest that is earned on principal that is reinvested to earn additional interest. So it's money that you've made by letting the money sit there in the bank, and you're going to gain additional money on top of that money you've already made. Okay? We have the compound interest formula. A equals P times the quantity 1 plus R over N to the NT power. Okay? A represents the future value of a loan. Okay, so it's how much money you're going to have later on if you just let that money sit there. P is called the principal, or sometimes we call it the present value. So it's how much money you have now. R is the interest rate. Okay, and for these problems, the interest rate will usually be given to you as a percentage. Okay, you'll need to go ahead and convert that to decimal form whenever you use this formula. N is the number of times compounded in a year. Okay, so which they'll tell you. Okay, so if you're compounding annually, N is 1. If you're compounding semi-annually, N is 2. If you're compounding quarterly, N would be 4. If you're compounding monthly, 12 months in a year, right? So N is 12. If you're compounding daily, you'd assume not a leap year. So N would be 365. Okay, it all revolves around 1 year. T is the time in years. Okay? And sometimes we have interest that's compounded continuously. Okay? So what that means is that you're compounding every second on the second. So not just like 4 times in the year, you're going to gain additional money, but every second on the second, you're going to gain additional money. Okay? The continuous compound interest formula is A equals P times E to the RT. So A is the future value, P is the present value, E meaning the number E, R is the interest rate, and T is the time, which is in years. Okay? So let's take a look at this example here. We want to find the future value if $10,000 is invested for 9 years at 4.3% compounded In part A, we're going to compound quarterly. And then part B, we're going to compound continuously. Okay, and then I'm going to mention some things afterwards. So in part A, because we're compounding quarterly, that's, you know, four times during the year, we're going to gain additional money on top of the interest that's already there. Okay, so we'll see how much money we'll have if we just let it sit there and do its thing for 9 years. Okay, P is $10,000. Okay, so I'm going to multiply that by 1 plus R is 4.3%. As a decimal, that would be 0.043. Make sure that you get the decimal correct also, you know, because the only reason I say that is because I see some people will write 0.43 for 4.3%. That's not true. Okay, there's no bank that's going to give you a 43% loan. Okay, or when you guys find the magical bank that does that, tell me about it, so I can put my money there. Okay, no bank's going to offer an interest rate that high. Divided by n. Okay, n is 4, combining quarterly, raised to the nt power. N is 4, t is 9. Okay, so then I would have to go to the calculator and type this in. Okay, let me go ahead and just do 1 plus 0.043 divided by 4 first. So if I do that, 1 plus 0.043 divided by 4, I'm getting 1.01075. Okay, and by the way, use all the digits that you see on the calculator. Okay, because when we get our answer, if there's any rounding, like you could be pennies off or you could be hundreds of dollars off. Okay, and when you have a problem like this, like I want it right down to the penny. If you're a penny off, I'm taking a point off. Okay, and that may sound kind of harsh, but you know, you got to think if this, well, like what if this is your money and you're investing it, and you know, the people that are doing the calculations, they're always pennies off, or in some cases they could be hundreds or even thousands of dollars off. Like, would that bother you? Or, I mean, it bothered me. Like if I were to call this 1.01, I would probably be pennies off. You know, so just use all the digits that you see on the calculator. Okay, and 4 times 9 is 36. So then the next thing is I'm going to raise that number to the 36th power, and okay, that's what I get. Okay, and then I'm going to multiply it by 10,000. Okay, so times 10,000, and it looks like I'm getting $14,695.18. Okay, by the way, there shouldn't be any issues with rounding, like you're working with money, right? So go near a cent on everything, round to the nearest two digits there. Okay, so if we just let the money sit there and you know, do its thing, in 9 years, this is how much money we'll have if we started off with $10,000. Okay, now in part B, it says, what if you're compounding continuously? Okay, well, I'm supposed to use the PERT equation, we sometimes call it. So P is $10,000 times E to the power R is 0.043, and then times T is 9. Okay, so how I would type this in would be, I should do 0.043 times 9 first, and you get 0.387. Okay, so then the next thing I would do is type in e to the power 0.387. Let's see, so second e to the power 0.387, and then hit enter. And that's the number that I got there. And then I'm going to multiply that by $10,000. Okay, so times 10,000, and I'm getting $14,725.56. Okay, so again, what it means to be compounding continuously is that you're compounding every second on the second. Okay, as opposed to like 4 times in the year or 12 times in the year or whatever. So when you compound it continuously, that is always going to be the formula that will give you the biggest output. Okay. Now I have to be honest, I have never ever seen a bank that offers interest compounded continuously. Okay, like there's no bank that I know of that's going to give you money every second of the day forevermore. Or when you find the magical bank that does that, tell me about that so that I can put my money there too. And we can both watch our money explode over time. Okay? Banks just don't do that, right? Like if you're putting money in a bank, usually they'll give you interest once a month, okay? Or like 12 times a year, okay? And even the the interest that you get is a couple of pennies or whatever. So anyway, I think that problems like this, where you're compounding continuously dealing with money, that's not a real world problem. That's not something that we see in everyday life, right? So a better example of this would be if we were going to study the population of the world, okay, and see how that's growing over time. Well, the population of the world is continuously growing. Continuously, that's a non-purpose word that I'm using. Okay, like every second of the day, there are thousands of births that happen all over the world, right? So, in a problem like that, it makes sense to use the PERT equation. It does not make sense to use this equation, okay? Because we don't have a start-stop thing going on. Like it's not like all of a sudden at one split second we got these these thousands of births happening, and then there's no activity for 3 months, and then all of a sudden after 3 months have gone by, then at one split second, then there's thousands of births that happen again, and then there's again no activity for 3 months. Like that doesn't happen, right? So it's a continuous thing. So because of it's a continuous thing, like it makes sense to use the continuous compound interest formula in a problem like that. Okay, we're going to do some more problems here, kind of towards the end of this chapter, dealing with this continuous formula, or the PERT equation. Okay, so there's going to be more on that, later. Okay, I have 2 more examples in the notes here. So anyway, why don't we stop the video right here, and I'll dig into those in the next video. Okay.